Okay, let's dive into this modelling task that we've been given. Real treat for us. Link to functions, because there's some functions working here, and hopefully a bit of crossover with what we've looked at previously with our GDC. So let's just take a time to just really have a good look at what's going on. Invite to spend 45 minutes. On the plan, A is south of B. A is south of B. Yeah, that makes sense to me. And C is east of B. C is east of B. Yep, okay. AB is 500 meters, so that's all labeled. BC is 300 meters. Engineers want to drill a tunnel from A to C. The tunnel has one or more straight sections. Okay, so we're dealing with straight sections. Calculate the length of the shortest possible tunnel from A to C. Give your answer correct to the nearest meter. Okay, to my mind, I'm looking at this and I'm thinking, well, we're going to have to go, oops, a straight line from A to C. Let me try that again. Straight line has got to be the shortest path, hasn't it? So can I do it with this tool? A to C, does that make it straight? Oh, look at that, that is straight. So that's got to be the easiest way. How do we achieve that? Well, that's going to be a right angle. So we're going to have a right angle triangle, Pythagoras. So let's write this out in full. 300 squared plus 500 squared equals the distance from A to C squared. So we could say that the square root of 300 squared plus 500 squared, that will equal the distance from A to C. Let's put that into our calculator then. So new calculator, square root of 500 squared plus 300, I've turned it the wrong way around, but it doesn't matter, it was all in my mind, 300 squared, and we're getting 583.095. Now let's look at the detail here. It asks us to the nearest, whoops, didn't mean to do that, it asks us to the nearest meter. So I'm getting 583.09, I'm going to round that to just 583 meters. Okay, write down the length of the tunnel if the engineers drill through as little hard rock as possible. Well, I'm thinking about this right angle triangle that I've created on my diagram, and what I'm thinking is, well, if this point were to move closer and closer to here, this hypotenuse across, for instance here, is going to get shorter. But as I continue that same idea, as I continue in this direction and going closer and closer, it continues to get shorter until it gets to B. So clearly the smallest amount of hard rock is going to be directly across this shaded section here. So it's going to be the 300 meters of hard rock. So the length of the tunnel in total, would be that 500 of soft or sort of normal rock plus the 300 of hard rock, which gives us a total of 800. Okay. Point P is a point which is x meters south of B. Okay, so we do have that labelled here, x. So the point P is from B to P. Might not be the best diagram for me, so I might just add on that is there to there. That's x. The engineers decide to drill from A to P to C. So the route they're taking from A to P to C. Okay. Through normal rock from A to P. Okay, so just clarifying though, it looks like it's on the edge of the hard rock. That is normal rock. The drill moves forward at 2 meters per hour. Through the hard rock from P to C, the drill moves forward at 1 meter per hour. Okay, so let's have a look at what's going on. Explain why the time it takes the drill to tunnel can be modelled by this equation. Well, let's just see if we can arrive at that equation. So we know that time, which is t, equals the distance divided by the speed, and that's what we're going to use. So I'm going to do it in two sections. Remember, my two sections were A to P and then P to C. So A to P, first of all, I need my distance, and that A to P was 500 in total. So I'm looking here. This 500, let me just get rid of it. This 500 minus this x. So 500 minus x is the distance. And the speed that I'm after, well, that was given to us at the bottom of the page. That was 2. So speed is 2. Well, that's quite nice. So AP, distance over speed, 500x over 2. So we're starting to piece this together. T equals 500 minus x over 2. Now, we've got that this section here is through, let's have a look, this section here, looking at a different bit now, this bit here is the hypotenuse of that right angle triangle. Again, we've got a shortened right angle triangle, but BPC is a right angle triangle, and we're interested in this hypotenuse. So I'm going to use the same techniques I used here to describe it. So that was the square root of x squared plus 300 squared. Let's go for this. So the distance, or what was it again? It was P to C. So PC, colon, the distance is the square root of 300 squared plus x squared. And 300 squared, so that is going to be the square root of 9 with 4 zeros plus x squared. And my speed is equal to 1. So therefore, I'm going to have add on to that the square root of 4 zeros plus x squared, and that's divided by 1, which I don't need to put on. So I might, because it's just encroaching on the other workings a bit, I might just box that off, and hopefully we've arrived at it. And hopefully that's enough of an explanation. So we're labeling the key terms and the expressions that we've got. We're labeling this as, no, don't do that. We're labeling this as being the distance. We're labeling this as the speed, and then for the other bit PC, we're labeling that this is the distance and this is the speed. And we've got this communication as well, that time is distance divided by speed. So hopefully all of that will piece together and make some sort of sense. Okay, part B. All the measurements are accurate. Write down a practical reason why the time given by the model may be different from the actual time. Lots of questions about this one. When I look at the mark scheme, it talks about anything that may hold it up. So I think the example that was given was changing the direction of the drill. So anything that in real life context, that would hold up and just alter the model slightly. Okay, part C. On the diagram, sketch the graph of t against x. Now I think it's worth just stopping at this point, because hopefully this is the point that we want to really identify and just spend a bit of time on, because if you got a little bit lost in the previous section, you can get back on at this point. All we're asking to do is to sketch the graph of t against x, and you've been given that formula here. So that's all we're going to do. We're going to sketch that graph and see what it looks like. So let's jump for my GDC. I need a new graph page, and I'm just going to put in exactly what it says. I need this as a fraction probably. So we've got 500 minus x over 2 plus square root, oh, that's the wrong one, let's delete that. That didn't delete very well, let's delete that. Okay, and it was a plus then, I've got this bracket I don't really need, okay, there we are, plus, now I want to, this is where it went wrong before, square root of 9, 2, 3, 4 zeros, plus x squared. And we plot the graph, and there it is in all of its glory. There's an issue going on here. Hopefully what you're noticing when you're looking at the axis here is we go from 400 to 600 and 0 to 500. So in order for us to get a good idea of what it is, clearly it's not going to be from 0 to 6.67. So we're going to change this. I'm going to do it by double clicking. 600 is what I want here. Now this one on the bottom, I actually want that to be 400. And we're going to go up to 500. There it is. Beautiful. Worth just noting at this point, I suppose, I'll move this out of the way, worth just noting what that intercept is, just to be sure when I'm looking at this axis here that I'm going through the right point. So if I want to be careful about that. So what have we got? We've got, let's go Control T to see our table of values, and when x is 0, it's 550. Okay, so I feel confident now putting in this at 550. Let me get the shape right. Look back at the shape, and I need to, yeah, okay, so it's going down and up like that. Not too bad. Okay, find the nearest meter to the position where P gives a minimum time. So worth just looking at what the variables are. So P minimum time. So we've got time, the position of P, 5 millimeters to the position of P. So P, just to give it context, was this point here. And that's been incorporated into the equation that we've done. So let's have a look at where this graph is at its minimum. So menu, analyze graph, we want the minimum point. It's somewhere between here and here. And we get 1.73510. So to the nearest meter, let's look at that again, nearest meter, that's distance in meters is my x coordinate, so I can read off that as 173. Oh, gone black. Maybe I'll go back to red. And find this minimum time. So time, remember, is the y coordinate. So the coordinate I can read off there is 510 hours. Okay. Part 4 then. To drill through normal rock costs $2,000 per hour. To drill through hard rock costs $3,000 per hour. Total cost of drilling the tunnel in N, $1,000. Okay, so that's N, so that's what we hope it looks like we're going to form an equation for. Write down a model for N in terms of X. Well, we know the distance. We know the time, don't we? That's what we have here. We have the time t. That's this t, the t that was given to us. We know that time. And it's saying how much it costs per hour. So it makes sense to simply use the time formula and apply it. Now what we need to recall is that this first section was soft rock and this second section hard rock. So soft rock is, let's write this out, soft rock is 500 minus x divided by 2, and that cost for every hour is $2,000. Now if we add to that 3 from here for the cost of hard rock times the time, which is 9 with 4 zeros again, plus x squared. I'm just a little bit cautious about this because my 3 here might be construed for a cube root. I'm going to make sure I communicate accurately, and it's 3 times that. Okay. Your answer may have been simplified. Great if you did. These 2's cancel, and we're left with 500 minus x plus 3 lots of 90,000 plus x squared square rooted. So let's have a look at this. Let's insert another graph. And we want to see what's going. The next question asks for the minimum cost. So let's graph it. Let's just see what happens. So we've got 500 minus x plus 3 times. You might come across an issue if you don't put in the times sign, strangely. The square root of 9, 1, 2, 3, 4 plus x squared. Just have a little look over that. It looks okay to me. And there it is again in all its glory. Clearly we've got an issue with the scales. Last time we went up to 600. Just going to put 1,000 to try and find it. We went across to 500 before. Let's put 1,000 again. See if we can find this graph. Ooh, I'm not finding it, am I? Let's try 1,500. Ah, here it is. Okay, so let's go menu. I think I can zoom box on this, can't I? No, window. Yeah, let's zoom box. Just see what's happening. So the first corner I'm going to put down here. Okay, so here it is. I've got my axis. I've got my equation. Let's just have a look. I don't need that anymore. Move this out of the way. We're after the minimum point, so let's just analyze this graph and have a look. Analyze graph for the minimum. Okay, what have I got coming out? I've got 106 and 1.35 e plus 3. Now let's just keep in mind what my x and my y are. X has always been a measure of, it should be down here, distance. So x is the distance, so we're finding to the nearest meter the position of P, which gives the minimum cost. Well, distance is measured in meters, so it suggests to me that I want the x coordinate here, and that's a little clue that I'm picking up. So that was quite an easy one, 106. And write in full the minimum cost to the nearest $10,000. So the cost is in terms of n, and that is this equation here that I've just plotted on my GDC. So that's going to be my y coordinate that I've got from that minimum point. So I got 1 point, that's not a very good point, 1.35 e plus 3. What does that mean? 1.35 times 10 to the power of 3, which is telling me it's 1,350,000. 1,350, and then I need to put in 3 zeros after that. So 1,350, 1, 2, 3, $1,350,000. Okay. We're nearly there now. The model for the time taken to drill the tunnel is T 500 minus x over 2. Yeah, we had that previously. That makes sense. The position of B and C are fixed. Okay, now to make sense of this, I'm going to have to refer back to the picture. The position of B and C are fixed. What does that mean? So, I'll erase all of this. So looking at this, B and C are fixed. Okay, that makes sense to me. Let's look at what the rest of it's saying. Investigate the position of P, which gives a minimum time when A is more than 500 meters south of B. When A is more than 500 meters south of B. Okay. That kind of makes sense. So that A, so this A is going to move down. and it's asking me what happens to the point P. So if this A moved down, the question is what happens to P. Okay. Right. Now it gives us a little clue here that we're dealing with this equation again. Now luckily I didn't close that document on my GDC, it's still here. Now I'm just looking into this, I'm looking at this equation that I've got previously, and if A were to move down, let's go back, if this here A moved down, then this value is going to be greater than 500. So let's see what happens when I change this. So to my mind I'm going to put in 550. Well, that's interesting, isn't it? Let's put in another value, 600 and 73560. Okay. Hopefully we're spotting a pattern. Let's try another one. 700, 173, 610. What stays the same? What always stays the same? Well, it's this 173. On all of those examples that I showed you, and you can pause, rewind, just have a look, I've spotted that this x coordinate stays at 173. So investigate the position of P. So we need to write this out somehow and communicate what we've just done. What we did was we moved as A moves further from P, the minimum time, so I like to quote exactly what the question's asking, the minimum time remains at 173. Okay, we're really close now. 5 part B, last couple of marks. If AB is equal to D meters, explain using part A why the minimum time in hours is T equals D over 2 plus K, where K is 260, correct of 3 significant figures. Okay, this seems a bit strange. It kind of looks similar to what we've got, but there's some strange notation going on. How am I going to piece this together? First thing, if AB is equal to D, we've just changed AB a lot of times. I changed it from 500, so this value here. I changed it as on my GDC from 500, 550, 600, 700. So now it's going to be in terms of D. So let's just write that out. So we get T is equal to now D minus X over 2 plus the square root of 9,000 plus X squared. The other thing we know that we've just found out is that the minimum time X stays at 173. So I'm going to try this at X equals 173. So what do I get? T equals D minus 173 over 2 plus root 9, all careful of this, 4 zeros, plus, not X anymore, 173 squared. Let's see what we get. So we get T is equal to, I can split this up to D over 2 minus 173 over 2 plus this thing, 173 squared. Okay. Let's put this into our calculator. Doc, insert a new calculator. So we need 173 over 2. Which gives me 86.5. So T equals D over 2 minus 86.5 plus, I need to put this one in as well, square root of 9, 1, 2, 3, 4 zeros, plus 173 squared, 346.3. 308. So I'm noticing I've got a positive and a negative here, so let's take that answer and I'll subtract the 86.5 to work out what these numbers are. So 259.8. So therefore I can, have I got any more space on this page? Nope. So I can squeeze this in, t equals d over 2 minus, now to three significant figures, that's going to be 260 3SF. And luckily, we've arrived at the answer we were looking to find. T equals d over 2 plus k, where k is 260. Oh, I've written that as negative. It shouldn't have been, that's just an error on my part. Nice to check though. And it's always good when you're putting your final answer just to give it the context of the question, and that sort of thing hopefully could be avoided. So we don't lose some marks there, which would be a real silly mistake to do, having done all that hard work. And there we are. Modelling task for this paper done. And now I need to work out how I stop the video. Okay. This is not part of the video. Stop screen.